For chapter 10, we're going to talk about rotational motion and angular momentum. Basically, this chapter is going to take everything we've already encountered as far as kinematics, forces, torque, and everything, and make it to where we have equations in place that takes into account rotational motion. We obviously know that with kinematics, everything's kind of linear and all that, but now we're going to take into account what if the object is spinning. We're going to expand on that concept there. So for starters, this figure shows uniform circular motion and some of its quantities. Remember that we discussed this back in chapter 6 briefly in gravitation. So we talked about how delta theta is equal to delta S over R, and our omega here is equal to delta theta over delta T. And so if we're taking these into account, we can say that our velocity is equal to our radius times our angular velocity. That's what our omega is. And we can obviously manipulate this to turn it into our velocity over r equals omega. And we also have our centripetal acceleration. Our AC is equal to our radius times our omega squared, or AC is equal to v squared over r. But AC is the centripetal acceleration towards the center of the actual object when our omega is constant. What if our omega is changing over time? Just like linear acceleration, we get then our angular acceleration. And that's going to be defined using alpha. Alpha is equal to our change in omega over our change in time. Just like our acceleration is equal to our velocity over time, this is our angular velocity over our time. So delta omega is equal to the change in angular velocity over the change in time. Since the units of omega are radians per second, then the units of alpha, our angular acceleration, are going to be radians per second squared. Also remember that there are 2 pi radians in a circle. That's just for understanding's sake. So suppose a teenager puts her bicycle on its back and starts the rear wheel spinning from rest to a final angular velocity of 250 revolutions per minute, or rotations per minute, in 5 seconds. Calculate the angular acceleration in radians per second squared. And if she now slams on the brakes, causing an angular acceleration of negative 87.3 radians per second squared, how long does it take for the wheel to stop? Okay, so for A, we're going to find our angular acceleration. So we are giving our 250 RPM over our time. So that's pretty straightforward there. But we know this is in RPM. We need to convert this into our radians. So we know that 250 revolutions per minute is equal to 2 pi radians over 1 revolution. This is coming from knowing that there's only 2 pi of a distance around the circle per 1 revolution. So if we're going 250 revolutions, we have to multiply that by 2 pi. And we know that we are in minutes, so we have to change that to seconds. So our angular velocity here is 26.2 radians per second. So once we plug that in, you simply get 5.24 radians per second squared. And for B, we're trying to find the time. So we use our angular acceleration equation, which is alpha equals delta omega over delta t, but we just switch these two. And we simply plug in negative 26.2 radians per second over negative 87.3 radians per second squared, which gives us 0.3 seconds. That's how long it's going to take for it to stop. If the bicycle in the preceding example had been on its wheels instead of upside down, it would first have to accelerate along the ground and then come to a stop. This connection between circular motion and linear motion needs to be explored. For example, it would be useful to know how linear and angular acceleration are related. In circular motion, linear acceleration is tangent to the circle at the point of interest, as seen in this figure. Thus, linear acceleration is called tangential acceleration, AT. So basically, we've all ridden a bicycle at this point around the wheel. Let's pretend it's the wheel of the bicycle. This is where our acceleration is. This is where our velocity is, right? So we are just identifying what that acceleration is. Linear or tangential acceleration refers to changes in the magnitude of velocity, but not its direction. We know from chapter 6 that in circular motion, centripetal acceleration, AC, refers to changes in the direction of the velocity and not its magnitude. An object undergoing circular motion experiences centripetal acceleration. Thus, our AT and AC, tangential and centripetal accelerations, are perpendicular and independent from one another. Tangential acceleration is directly related to our angular acceleration, which is our alpha, and is linked to an increase or decrease in the velocity, but not its direction. Now we can find the exact relationship between the linear acceleration, AT, and angular acceleration, alpha. Because linear acceleration is proportional to a change in the magnitude of its velocity, it is defined as in one-dimensional kinematics to be AT is equal to our change in velocity over change in time. For circular motion, note that our velocity here is RW. Our radius times our angular velocity. So if we were to substitute that RW for velocity, we end up with this, where we have our change in radius omega over change in time. All we're doing from this step to this step is taking away the radius because we know that the radius is fixed. Our radius is constant. That's not going to change. So we're simply just putting the change, the del, or the delta, together with the omega. So by definition, we know that our alpha is equal to our change in omega over change in time, which is exactly what we have here. So we have our tangential acceleration is equal to r alpha, or our alpha is equal to our tangential acceleration over r. These equations mean that linear acceleration and angular acceleration are directly proportional. The greater the angular acceleration is, the larger the linear tangential acceleration is, and vice versa. For example, the greater the angular acceleration of a car's drive wheels, the greater the acceleration of the car. The radius also matters, obviously. For example, the smaller the wheel, the smaller its linear acceleration for a given angular acceleration alpha. That brings us to here. A powerful motorcycle can accelerate from 0 to 30 meters per second, about 108 kilometers per hour, in about 4.20 seconds. What is the angular acceleration of its 0.32 meters radius wheels? So we have our velocity and our time, and we also have our radius. So we're looking for acceleration. We have velocity over time. That's 30 over 4.2 gives us 7.14. And we're looking for our alpha, right? So we have our tangential acceleration, 7.14, divided by our radius, 0.32. And that's simply just 22.3. That one's just plugging in the numbers for where they belong. So here's a summary of what we know so far. We know our theta is basically our x, and the relationship between them are theta equals x over r. Our omega is basically our velocity, and we know that the relationship between them is omega equals v over r. And we know our alpha, which is basically our acceleration here, and that is our alpha is equal to our acceleration over r. So you notice that between the transitions, all we're really doing is dividing by the r. Kinematics is the description of motion, as we know. The kinematics of rotational motion describes the relationships among rotation angle, angular velocity, angular acceleration, and time. Let us start by defining an equation relating omega, alpha, and t to determine this equation. We recall a familiar kinematic equation for transitional or straight line motion. V equals V naught plus AT, where our constant A. Note that the rotational motion, A is equal to AT, and we shall use the symbol A for tangential or linear acceleration from now on. As is in linear kinematics, we assume A is constant, which means that our angular acceleration, alpha, is also constant, because A is equal to radius alpha. So if our alpha is constant, we already know our radius is constant, that means our acceleration is constant. Note, now let us substitute V is equal to R omega, and A is equal to R alpha into the linear equation above. So that gives us our omega from our velocity is equal to our omega naught from up there plus our alpha from our A times our time. Well, the radius cancels all the way through, right? There's a radius in each variable there. So we are left with omega is equal to omega naught plus alpha t, where we know omega naught is the initial angular velocity. This last equation is a kinematic relationship between alpha, or omega alpha, and time. That is, it describes the relationship without reference to forces or masses that may affect rotation. It is also precisely analogous in form to transitional counterpart. So if we're able to do this with all of the kinematic equations, you'll pretty much get this, where we have our theta is equal to omega t, which is basically x equals vt. The equation we just went through, omega equals omega naught plus alpha t. Our theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared, which is basically our x equals x naught plus b naught t plus 1/2 at squared. We also have omega squared is equal to omega naught squared plus 2 alpha delta theta, which is our v squared equals v naught squared plus 2a delta x. And finally, we have our average omega is equal to our omega naught plus omega over 2, which is our velocity average is equal to velocity naught plus velocity final, basically, over 2. So basically, we can go from transitional to rotational pretty much by just substituting. That brings us to example 10.3. We see that we have a radius of 4.5 centimeters right there. We have a real fishing line. Rotational quantities are theta, omega, and alpha. The direction of motion is given, and our linear or transitional quantities is pointing in that direction, x, v, and a. A deep sea fisherman hooks a big fish that swims away from the boat, pulling the fishing line from its fishing reel. The whole system is initially at rest, so we know our velocity is 0 and our angular velocity is 0. And the fishing line unwinds from a reel at a radius of 4.5 centimeters from its axis of rotation. The reel is given an angular acceleration of 110 radians per second squared for 2 seconds as seen above. For A, what is the final angular velocity of the reel? For B, what is the speed in the fishing line leaving the reel after 2 seconds elapse? For C, how many revolutions does the reel make? And D, how many meters of fishing line come off the reel in this time? All right, so for A, we have our alpha and t are given, and omega needs to be determined. The most straightforward equation to use is omega is equal to omega naught plus alpha t, because we know that omega naught was 0. So we plug in basically what we know. We are given our alpha. We know that it's from rest, so we know omega naught is 0, and we're given our time. So plug that in straight through, you get 220 radians per second. So now that we know that, we can find our velocity. So that's just our radius times omega. So our radius is 0.045 meters after we convert it. And we know 220 is our omega, so 990 meters per second. For C, we get to use the bigger equation. Here we are asked to find the number of revolutions. So theta is our angle. We're going to go ahead and use that one. So we know that it's initially a 0, and we need our 1/2 is 0.5 here. Our alpha is 110 radians per second squared, and our time is 2 seconds squared. So that equals 220 radians. Converting that from radians to revolutions, which is dividing by 2 pi, gives us 35 revolutions. And for D, the number of meters of the fishing line is x. So we know our theta, given here. And here we're going to use our 220. And we're going to use our radius, obviously 0.045 meters. And that's just 990. And you see how the 220 here for our theta is the same as our radians per second. And you see that 990 meters is also 990 meters per second here. If you have ever spun a bike wheel or pushed a merry-go-round, you know that force isn't needed to change angular velocity. In fact, your intuition is reliable in predicting many factors that are involved. For example, we know that a door opens slowly if you push it too close to its hinges. Furthermore, we know that the more massive the door, the more slowly it opens. The first example implies that the farther the force is applied from the pivot, the greater the angular acceleration. Another implication is that the angular acceleration is inversely proportional to its mass. These relationships should seem very similar to the familiar relationships among force, mass, and acceleration embodied in Newton's second law of motion. There are, in fact, precise rotational analogs to both force and mass. And now we're going to be talking about forces. So to develop the precise relationship among force, mass, radius, and angular acceleration, convert what happens if we exert a force F on a point mass m, that is a distance r from a pivot point. So we have force, mass, and distance. Because the force is perpendicular to the r, a radius, and acceleration a is obtained in the direction of force. We know that F equals ma, and so how do we put this in terms of rotation? Well, we know that a is equal to r alpha, and if we substitute that into our F equals ma, we get F equals ma, which equals r mr alpha. Recall that torque is turning effectiveness of a force. In this case, because F is equal to perpendicular to r, torque is simply our tau is equal to F r sine theta, which is equal to Fr sine 90 because it's perpendicular, so Fr. So if we multiply both sides of the equation above by r, we get torque on the left side hand. That is, our tau is equal to Rf, but we know our F now is equal to mr alpha from above. So we get two radiuses, so we get mr squared times alpha. This last equation is a rotational analog of Newton's second law, F equals ma, where torque is analogous to force, angular acceleration is analogous to transitional acceleration, and mr squared is analogous to mass or inertia. The quantity mr squared is called the rotational inertia of, or moment of inertia, of a point mass m, a distance r from the center of rotation. To expand on our concept of rotational inertia, we define the moment of inertia I of an object to be the sum of mr squared for all of the point masses of which it is composed of. That is, our I is equal to the sum, that's the summation symbol, mr squared, where I is analogous to m in transition of motion. Because of the distance r, the moment of inertia for any object depends on the chosen axis. Actually, calculating I is beyond the scope of this class except for one simple case, that of a hoop, which has all of its mass at the same distance from its axis. A hoop's moment of inertia around its axis is therefore mr squared, where m is the total mass of the hoop and r is the radius. We use big size m and big size r for the entire object to distinguish them from little m and little r for point masses. In all other cases, we must consult the following figure in the next table for formulas I that have been derived from integration over the continuous body. Note that I has the units of mass multiplied by the distance squared, kilograms times meter squared, as we might expect from its definition. The general relationship among torque, moment of inertia, and angular acceleration is found to be our net torque is equal to our Rf is equal to mr squared alpha. So mr squared is our I. So we know that alpha is equal to net tau torque divided by I, where net torque is the total torque from all forces relative to a chosen axis. Such torques are either positive or negative and add with like ordinary numbers. This equation is actually valid for any torque applied to any object relative to any axis. So here are all the different equations for our rotational inertia. We see that a hoop, like we mentioned, is I equals mr squared. If you're talking about a solid cylinder, about the center of its axis, it's mr squared over 2. We're talking about a thin rod, about its axis, center perpendicular to the length, so down the middle instead of through the actual cylinder. Talking about ml squared over 12. A solid sphere about any diameter is 2mr squared over 5. A hoop, but down the middle instead of through its center, is I equals mr squared over 2. Annular cylinder or a ring about cylinder axis is big M over 2 times R1 squared plus R2 squared. Solid cylinder or disk about the central diameter. So you have I is equal to mr squared over 4 plus ml squared over 12. A thin rod about axis through 1 and perpendicular to the length. So at the very back of this one would be big M L squared over 3. A thin spherical shell about any diameter is about 2mr squared over 3. And a slab about axis through the center. So that's m a squared plus b squared over 12. But for this class, we're going to focus on that hoop, the mr squared, easy one. So for this example, consider the father pushing a playground merry-go-round. He exerts a force of 250 newtons, so we have our force, about an edge of 50 kilogram mass. A merry-go-round, which has a radius of 1.5 meters, r. Calculate the angular acceleration produced for A, when no one is around the merry-go-round, and B, when an 18 kilogram child sits 1.25 meters away from the center. Consider the merry-go-round itself to be a uniform disk with negligible friction. Okay, so we know that our alpha is equal to our tau over I, where we have our tau, which is the force that we're looking for here. Well, we're calculating the angular acceleration, but for that we need our tau. So we have our force and our radius, and we know it's perpendicular, pushing perpendicular to the surface here. So 1.5 times 250, and that's the amount of torque that the father's pushing. So for the moment of inertia of a solid disk, we have 1/2 mr squared, where our mass is 50, our radius is 1.5. So our moment of inertia, which is I, is 1/2 times 50 times 1.5. That gives us 56.25 kilograms per meter squared, or times meter squared. So if we're able to plug this into the original equation, tau over I, we get 375 over 56.25, which is 6.67 radians per second squared. So the trick here would be just knowing that this is the original equation you're going to use. Now you have to find your torque and your moment of inertia. So here, now we have a child sitting in on the merry-go-round, which we're going to treat as a point mass. So just a point. We know that it weighs about 18 kilograms and is about 1.25 meters away. So since we're talking about a point mass, it's just mr squared. That's 28.13 kilograms meter squared. So we have 28.13 plus 56.25. That's 84.38. Because remember, we need to have the summation of the moment of inertia. So we have to include the child plus the moment of inertia the father's putting. So now that we have that, our total torque is still 375. The child's not doing anything to add any force. So we're just going to do 375 over 84.38, and that is 4.44 radians per second squared. So the difference there was just knowing that the child that's on the merry-go-round now is just treated as a point mass, nothing else. So that brings us to kinetic energy, rotational kinetic energy. Work must be done on rotational objects such as grindstones or merry-go-rounds. Work was defined in Chapter 7 for transitional motion, and we can build on that knowledge when considering work done in a rotational motion. The simplest rotational situation is one in which the net force is exerted perpendicular to the radius of a disk, as shown in the figure, and remains perpendicular as the disk rotates. The force is parallel to the displacement, and so net work is the product of the force times the arc length traveled. So arc length here is a displacement. Remember, we transition from our x to our displacement. So we have our net work is equal to our net F delta S. If we translate force into torque, the rotational equivalent, and the arc length displacement into our theta, we get net work is equal to our R net F delta S over R. But we know that R net F is our net torque and our theta, which is just delta S over R. So we end up getting that our net work here is I alpha theta. So since the net torque is equal to I alpha. Using the work energy theorem and the rotational kinematics equations from earlier, we can see that this work causes a rotational motion of any object that rotates. This means we can define a rotational kinetic energy that has the form Ke for rotational is equal to 1/2 I omega squared. So using this, consider a person who spins a large grindstone by placing her hand on its edge and exerting a force as shown. How much work is done if she exerts a force of 200 newtons through a rotation of 1 radians? The force is kept perpendicular to the grindstone that has a 0.32 radius at the point of application, and the effects of friction are negligible. For B, what is the final angular velocity, if the grindstone has a mass of 85 kilograms? And C, what is the final rotational kinetic energy? It should equal to our work. Okay, so our net work, which is what we're looking for here, how much work is done. So we know our net work is equal to our net torque times our theta. So we know that torque is Rf, and we know that it has a radius of 0.32, and we know our force is 200, and our theta is our 1 radian. So we multiply that straight through, and it's 64. 64 newtons per newtons meter, and we note that 1 newton meter is equal to 1 joule. So remember, we have to transition that because now we're talking about work. We're talking about energy. So 64 joules. And for B, now we are looking to find our final velocity, final angular velocity. So we have omega squared is equal to omega naught squared plus 2 alpha theta. So we know it started from rest, so it's 0 for omega naught squared. So we have, all we have to do here is really just square root it. This is 0, so square root 2 alpha theta. So we still have to find our alpha though. Well, we know that our torque, which we have, is 64 newtons per meter from above. And we have to find our I to find our alpha. So the moment of inertia found for this cylinder here, 1/2 mr squared, which is equal to 0.5, just from the 1/2, times our mass given, which is 85, times our radius, 0.32 squared. So that's 4.32352 kilograms meters squared. So now we substitute this I into our alpha equation to find alpha. So alpha is equal to 64 over 4.352. So that's about 14.7 radians per second squared. So now that we have that, we plug it into the original equation we found using this kinematic equation. And we just plug in 2 times 14.7 times our theta, 1. Square root of that. So that's 5.42 radians per second. And so finally, we're going to find our final rotation and kinetic energy. So 1/2 I omega squared. Well, we find our I up here whenever we were solving for alpha, so 4.352. And we need our omega. Well, our omega here, where do we solve for omega? Oh, right here. That's 5.42 radians per second. So 0.5 times 4.352 times 5.42. So that's 64 joules, which makes sense because this has to equal the work that is put in. Remember, work and energy, if they're conserved, which they should be in the work energy theorem equation, they should always equal each other. So another example, calculate the final speed of a solid cylinder that rolls down 2 meters high incline. The cylinder starts from rest, has a mass of 0.75 kilograms, and a radius of 4 centimeters. Here it is. So for here, we know that it's starting from rest. So we have our potential energy, right? Because it's starting from rest. There is no kinetic energy on the left side. And on the right side, we know that it's rolling down. So we know that there is some energy, some kinetic energy. But now we also have to take into account our rotational kinetic energy. So that's why you have our 1/2 mv squared, which is our kinetic transitional energy, and 1/2 I omega squared, which is our rotational kinetic energy. So from here to here, all we're doing is finding our I. Our I here for our cylinder is 1/2 mr squared, and our omega is v squared over r squared. Well, if you notice, the cylinder's radius and the mass cancel. So mass cancels here, and the r squared cancels. So we are left with GH is equal to 1/2 v squared from here, plus we have our 1/4 v squared left, and our m canceled, r squared canceled, r squared canceled. So this just equals 3/4 v squared. And that's exactly what we're looking for. We're looking for our velocity. So everything else kind of cancels out conveniently. So we just equal it to our velocity. So multiply 3/4 by 4/3 to get it on the other side, and square root. And we have all that. So 4 from the fraction times 9.8, which is gravity, times our 2 meters, which is the incline, over 3, which comes from the fraction. Square root that, and you get 5.11 meters per second. So the convenient part here was that the m and the r canceled out. So the math was just pretty simple. If you wanted to, you could still keep the masses there, but conveniently we could just cancel them out from the very beginning. Okay, so now we start with angular momentum. By now, the pattern is clear. Every rotational phenomenon has a direct translational analog. It seems quite reasonable then to define angular momentum, L, big L. L is equal to I omega. This equation is an analog to the definition of the linear momentum, which is P is equal to mv. Units for linear momentum are kilograms meters over seconds, while units for angular momentum are kilograms per times meter squared over seconds. So the squared difference there for the math, or for the meters. As we would expect, an object that has a large moment of inertia I, such as Earth, has a very large angular momentum. An object that has a large angular velocity omega, such as a centrifuge, also has a rather large angular momentum. When you push a merry-go-round, spin a bike wheel, or open a door, you exert a torque. If the torque you exert is greater than the opposing torques, then the rotation accelerates and the angular momentum increases. The greater the net torque, the more rapid the increase in L. The relationship between torque and angular momentum is given by our net torque is equal to our change in angular momentum over change in time. This expression is exactly analogous to the relationship between force and linear momentum, which is just F is equal to our change in momentum over change in time. The equation for net torque is change in angular momentum over change in time is a very fundamental and broadly applicable. It is, in fact, the rotational form of Newton's second law. So, just like in any case in linear momentum, we can see that if the net torque on an object is 0, then the angular momentum must also be conserved. This is the law of conservation of angular momentum, and it says that as long as the net torque is 0, the total angular momentum is constant. So, for example, 1014, suppose an ice skater, such as the one above, is spinning at a 0.800 revolutions per second with her arms extended. She has a moment of inertia of 2.34 kilograms meter squared with her arms extended, and a 0.363 kilograms meter squared with her arms close to her body. These moments of inertia are based on reasonable assumptions about a 60 kilogram skater. So there's our mass too. For A, what is her angular velocity in revolutions per second after she pulls in her arms? And B, what is her rotational kinetic energy before and after she does this? So, because the torque is negligible, the conservation of angular momentum given is I omega is equal to I prime omega prime and is applicable. So our initial angular momentum is equal to our angular momentum prime. And that's basically what we just said. So we're going to find our omega prime, which is going to be I over I prime omega. So we have our 2.34 before she extends her arms, and then after 0.363 times our initial angular velocity. So that equals 5.16 revolutions per second. And that is what is her angular velocity in the revolutions per second after she pulls in her arms. So for B, now we're going to find our rotational kinetic energy. So we have a 1/2 I omega squared for our equation, obviously. So the initial value is found by substituting the known values into the equation, converting the angular velocity to radians. So we have to convert our 0.8 revolutions per second to our radians. So we just multiply by 2 pi. And we take into account the initial angular momentum, or moment of inertia. So once we do all that, we get 29.6 joules initially. And our final rotational kinetic energy, we do the same thing. Get our 5.16 revolutions per second, which we just found. Multiply that by 2 pi, and multiply it by our moment of inertia. That gives us 191 joules. So here in both parts, there is an impressive increase. First, the angular velocity is large, although most world-class skaters can achieve spin rates about this great. Second, the final kinetic energy is much larger or much greater than the initial kinetic energy. The increase in rotational kinetic energy comes from the work done by the skater in pulling in her arms. This work is internal work that depletes some of the skater's food energy. So just because she pulled in her arms, that radius, if you think about it, came in closer. So that energy that she had was more stored in closer to the center of mass. All right, so the solar system, for an example, coalesced from a cloud of gas and dust that was originally rotating, so from A to B to C. The orbital motions and spins of the planets are in the same direction as the original spin and conserve the angular momentum of the parent cloud. That's just an example. So for 10.15, we have a mass, little m, times our velocity. That the disc hits our big M, and we have our nail as our pivot point, and we know that after it's going to go in a rotation. So for A, disc slides towards a motionless stick on a frictionless surface, and B, the disc hits the stick at one end and adheres to it, and they rotate together, pivoting around the nail. Angular momentum is conserved for this inelastic collision because the surface is frictionless and the unbalanced external force at the nail exerts no torque. So suppose the disc has a mass of 50 grams and the initial velocity of 30 meters per second. When it strikes the stick, that is 1.2 meters long and 2 kilograms. What is the angular velocity of the two after the collision? What is the kinetic energy before and after the collision? And what is the total linear momentum before and after the collision? So our strategy for A is that we can answer the first equation by using conservation of angular momentum as noted. Because the angular momentum is I omega, we can solve for the angular velocity. So we have L is equal to I omega. And we know that the mass, or the disk, is going to be kind of like a point mass. So we have our I is equal to mr squared, taking the disk to be approximately a point mass. And we have our omega is equal to VR. So from here, L equals I omega, we end up with L is equal to mr squared from our I times our V over R from our omega. Well, one of the r's cancel, so we're left with mvr. And after the collision, we have L prime is equal to I prime omega prime. So it is W prime that we wish to find here. So we just simply solve for it right there. And we know that after it's going to be mvr. This is after the collision. Where I prime is the moment of inertia of the stick and the disc stuck together, which is the sum of their individual of inertia about the nail. So figure 1012 gives the formula of a rod rotating around one end at I is equal to mr squared over 3. Thus, we have our I is equal to mr squared from our disk plus mr squared over 3. So that's m plus m over 3 r squared. So once we plug all of our masses together here, we have 0.05 kilograms and 0.667 kilograms from converting our grams to kilograms times our 1.2 meters squared. So that's 1.032 kilograms meters squared. So now we have our I, we enter it back into our original equation here. So our omega prime is MBR, 0.05 kilograms times meters, or 30 meters per second, times our 1.2 meters over 1.032. That gives us 1.744 radians per second. So we just round up there. And this equation here is from the original equation over here. So for B, the kinetic energy before the collision is the incoming disk transitional kinetic energy, and after the collision, it is the rotational kinetic energy of the two stuck together. So originally, the disk was just moving in a linear fashion. So we do our regular linear kinetic energy. So 0.5 times 0.005 times 30 squared. So that gives us 22.5 joules. After the collision, they stick together. So we have our 1/2 I prime omega prime squared, and we just found our I, 1.032 kilograms meter squared, times our omega prime, which we just found as well, 1.744 radians per second squared. That gives us 1.57 joules. That was pretty straightforward because we just solved everything up there. So for C, find the linear momentum before and after the disk collision. So P is equal to mv. We have our mass of our disk, 0.05 kilograms, and our velocity of it, 30 meters per second. So that gives us 1.5 kilograms times meters per second. But after the collision, the disk and the stick center of mass move in the same direction. The total linear momentum is that of a disk moving in a new velocity v prime, which is equal to r omega prime, plus that of the stick center of mass, which moves at half the speed because our velocity of our center of mass is equal to r squared, or r over 2 omega prime, which is v prime over 2. So after the collision, we end up with mv squared plus big M v center of mass. So point mass, center of mass. So we end up with transitioning from here to here, pulling our v squared out, ends up with this. We know our v squared, or our v prime, I mean, is really our r omega prime. So we are able just to substitute everything in. So we end up with 1.05 kilograms for our two masses, divided by 2 here, times of 1.2 meters from our radius, times our 1.744 from our omega prime. So that just simply gives us 2.20 kilograms meters over seconds. So that's our before and after momentum. And that'll do it for chapter 10. Please contact me if there's any questions.